Hey guys, this is Mrs. Lyons. Time for a little chemistry. I'm going to go over, there are 3 pages in your packet that talk about endothermic and exothermic situations, processes, reactions, equations. And we need to be able to tell the difference between exo and endo. Okay, so we have 2 examples here. One is ice melting, and the other is water freezing. So what we want to do with this is we want to identify which way the energy is moving, which way is heat being transferred. Okay, and remember that heat or energy always moves from from warm to cool. Okay, so for example, we have this ice cube. We know that water freezes at 0 degrees Celsius. Okay, the air in our house is about 25 degrees Celsius or so. Okay, so the room is warmer than the ice cube, and it's warmer than the ice can stay frozen. All right. So what happens is the energy from the air in the room moves into the ice cube, causing it to melt. So since the energy is moving in, that is an endothermic process. Okay. So of course, water freezing is the opposite. So we could just very easily say, okay, well, if this is endo, this must be exo. But let's think about the why. Okay. So if you run water into your ice cube trays, that water is probably, I'm going to say maybe 20 degrees ish, depending on what you have your tap set. When you put ice in the freezer, okay, the freezer is at 0 degrees Celsius or lower. Okay, so remember, if energy moves from warmer to cooler, the energy is going to move from the water out into the freezer. Okay, so this makes this an exothermic reaction. All right, so now if we look at the next 2 questions, this says for each of the chemical equations listed below, determine the delta H value and identify the reaction as endothermic or exothermic. Okay, so basically what we need to know to answer this question, we need to know a couple of things. We need to know that in an exothermic process, okay, the kilojoules, so energy, let's put kilojoules, is on the product side. Endothermic energy, or kilojoules, is on the reactant side. The other thing that we know is with an exothermic equation, we have a negative delta H. With an endothermic equation, we have a positive delta H. Okay, so if I look at this reaction, we have hydrogen plus iodine plus 50.16 kilojoules produces hydrogen iodide. Okay, so the energy is on the reactant side. Okay, so the first thing we can say is because it's on the reactant side, this is an endothermic reaction. Now it asks me to write, just tell what is delta H. Okay, so delta H is going to be 50.16 kilojoules. We need to know, is that positive or negative? Since this is an endothermic equation, reaction, the delta H is going to be positive. Okay, letter B. Carbon plus oxygen produces carbon dioxide and 393 kilojoules. Okay, so since our energy is on the product side, I know that this is going to be an exothermic process. And if I want to write my delta H is going to equal 393.51 kilojoules. Okay, since this is exothermic, delta H is going to be negative. So it's going to be negative 393 kilojoules. Okay, what that means is 393 kilojoules of energy was produced and exited the system in this reaction. So if you were to do this reaction and you were to do it in a test tube or a flask and you could touch it, the flask would feel hot. Okay. Second, rewrite each of the chemical equations below with the delta H value included with either the reactants or products. Okay, so basically this is asking us to rewrite this equation and put the energy in on the right side. Okay, since we have a negative delta H, that tells us that this reaction is an exothermic process. So what that means is when I write my thermochemical equation, I'm going to include the energy on the right side. Now notice something. When I put this energy into my reaction, even though it's a negative value, it goes in as plus 1200 kilojoules. Okay, the fact that it's in the product is what tells us that this is exothermic and that it would be negative delta H. Okay, so here we have iodine, and this is an interesting thing. I don't know if you pay attention, but what this says is we have iodine as a solid, and that transforms to iodine as a gas. Okay, so and this tells us that 62.4 kilojoules of energy is put into or absorbed into the reaction, okay, into this process. So if I rewrite this, I'm going to write I2 solid plus 62.4 kilojoules is equal to I2 gas, okay? And this is an endothermic process. Okay, so let's look at the next page. Whoops. All right, let's just go through these examples too while we're at it. So when sodium bicarbonate is added to hydrochloric acid, the resulting solution is warm to the touch. Is this process exothermic or endothermic? This process is going to be exothermic, and it's going to be exothermic because heat is moving from the system to the surroundings. So when you touch the test tube or the flask, it feels warm to the touch because heat is coming out of the reaction. All right, here we go, some more examples. Determine the delta H. Okay, so here our energy is on the left side of the arrow, which means that our delta H is going to be positive. So positive 89.3 kilojoules. Okay, when our energy is on the product side, that tells us we have an endothermic reaction. Okay, so energy is going from the surroundings into the system. Okay. Second example, we have our energy on the on the product side. So when we write this as a delta H, we say delta H is minus 26.3 kilojoules. And since delta H is negative, this is an exothermic example. All right. Rewrite the equations. Okay, so negative 13.68 kilojoules tells me this is an exothermic equation, and I need to rewrite it. So I'm going to say C2H5OH plus 3O2 produces 2 carbon dioxide plus 3 water plus 1368 kilojoules. Okay, so we put the energy on the product side because the reaction is producing energy and energy is moving from the system to the surroundings. All right, here we have another phase change. We have solid water going to liquid water, okay? And the delta H is 6.01 kilojoules. So excuse me, if I rewrite this, I'm going to write H2O solid plus 6.01 kilojoules produces H2O liquid. And this is an endothermic reaction or process. Okay. Now, number 4 tells us to draw an enthalpy diagram. So we're going to draw 2 enthalpy diagrams. Okay. For A, and this is your first time probably drawing one of these. I've given you kind of the backbone, but some things to remember. Okay. The x-axis is the reaction progress. Okay, so time essentially. At time 0, that's where we mix our chemicals together and our reaction gets started. The y-axis is energy. All right, so in this case, delta H is 392.2 kilojoules. What that tells me is this is an endothermic reaction. Now, here's what I want you to remember, okay? I don't need you to put numbers on your graph, okay? Basically, what I'm looking for when you draw an enthalpy diagram is, are your reactants in the right place relative to the products, okay? So in an endothermic reaction, okay, and we're going to write this down, the energy of the reactants is lower than the energy of the products. So essentially, I'm going to draw my line for my reactants. Remember, we're always going to start with our reactants. We combine them. And when we combine them, our graph changes. So we kind of have this beginning point when the reaction is getting started. And then we go up, we have this, what we call activation energy. Okay, and we'll get to that in a minute. But in an endothermic reaction, the energy of the reactants is lower. Okay, so it's down here. This is up higher than the energy of the products. Okay, so that's what we are talking about. Now, something else that you have to label is the activation energy. Okay, remember the activation energy we call E sub A, and the activation energy is the difference between the reactants and the peak. Okay, so if I'm looking at this graph, the activation energy is from the level of the reactants all the way up to the peak of our graph. That's our activation energy, which we specify as E sub A. Okay, and then the other thing that we need to make a note of on our graph is the change in enthalpy. Okay, let me make this a little bit darker. It's hard to see. Okay, so activation energy is from reactants to the top. Okay, delta H is the change in enthalpy. Okay, and remember that the change in enthalpy is the difference between reactants and products. So I'm going to draw a line from the energy level of my reactants up to my products. Okay. And this amount of energy is called delta H. And notice that I started at the reactants and I went up. So I was increasing. That tells me that delta H is positive, okay, because we're going up. And it's an endothermic reaction, okay? So let's look at, and notice I didn't spend any time worrying about how far the reactants and the products were from each other or how high the activation energy. What I'm really looking for in this situation is that you know the basic shape of the enthalpy diagram. Okay, so now we're going to draw a second enthalpy diagram. Okay, and in this case, our energy is on the product side. So this is going to be an exothermic example. Okay, and I'm going to have to draw it small because I didn't leave us a lot of room. Okay, but we can say our xn progress, PROG, right? Reaction progress and energy are our axes. We're going to start with our reactants. Okay, in an exothermic reaction, okay, the reactants are at higher energy than the products. Which means if this is my reactants, my products are going to be over here somewhere at a lower energy level. Okay. And then the way that I get from reactants to products is I've got to go up, you know, that activation energy, the amount of energy it takes to get the reaction going. And then I drop down to where the energy level of my products. Okay. So let's look at activation energy. Whether it's an endothermic or exothermic graph, activation energy is the difference between the reactants and the peak. Okay, so in this case, my reactants are here. So my activation energy is much smaller. Okay, because it's going from the reactants to the peak. My delta H, my change in enthalpy, is going from the reactants, the energy level of the reactants, to the products. Okay. Now, if I draw the arrow from the reactants down to the products, I'm going down. Delta H is negative for an exothermic reaction. All right. So I think that takes us through a couple of the examples. Oh, you know what? We are going to go ahead. There's one more practice sheet in here. I'm just going to put these all in the same video just so that you can kind of fast forward through them and see what's going on. Okay, so draw arrows showing which direction the heat is being transferred. Okay, so we've got a pot of boiling water and we've got a fire underneath it. Okay, and the water is starting to boil. All right, so we got to think about what makes water boil. Does energy move into the water, or is energy absorbed out of the water? And hopefully what your answer is that energy is put in. We have to heat up the water in order for it to boil. Okay, so this process is endothermic. Okay, we have to put energy in to get water to go from liquid to gas. All right, let's see. When ammonium nitrate is mixed with water, the resulting solution is cool to the touch. All right, that means this is an endothermic process. Remember, in an exothermic process, you feel the heat coming out of the reaction, while in an endothermic reaction, it feels cool to your touch. So energy from the room is being absorbed into our system. Here's a great example of what I mean when I want you to be able to look at an enthalpy diagram and tell me, is it exothermic or endothermic? Okay. In this case, the energy level of the reactants is lower than the energy level of the products. So this is an endothermic reaction. All right. And then we're supposed to label reactants, products, activation energy. So activation energy is going to be, as you know, hopefully you're getting the hang of this, from the reactants to the very tippy top of the graph. That is my activation energy. And then delta H, the change in enthalpy, is the difference between the reactants and the products. And since we're going up from the reactants to the products, delta H is positive. Okay. All right, let's see. Rewrite the chemical equation. Okay, so this is another where we have to put the value into the equation. So Pb plus 2Cl2, this is a negative energy value, which means we have an exothermic reaction, and energy is going to be shown in the products. Okay, so we've got lead plus chlorine reacts to give us lead 4 chloride plus 392.2 kilojoules of energy is released. All right. Guess what? We had an exo, we're going to have an endo. Okay, in an endo reaction, we have 2MgO plus 285 kilojoules produces 2 magnesium plus oxygen. Okay, so we put that energy, because it's a positive delta H, we put that energy on the reactant side. Okay, let's see, determine the delta H. So in this case, delta H is going to be 182.4 kilojoules. Is that going to be positive or negative? It's on the left side of the arrow, so that makes this an endothermic process. And then part B, delta H, is 484 this should be kilojoules. I don't know what that was. Kilojoules. And since it's on the product side, that's going to be minus 484 kilojoules. Okay, so that is going to be an exothermic process. All right, so that just took us through some practice of exo and endothermic, some enthalpy diagrams. I hope that was helpful. Have a wonderful day, night, whatever, whenever you're listening to this. I hope it's good. I will see you in class. Take care of yourselves.